Welcome back to The Explainer. We spend a ton of time talking about the massive engines inside modern ships, but today, we're focusing on the incredible system that actually gets those giants moving. We're going to demystify the ship's propulsion system, specifically the journey from the engine all the way out into the ocean. It is an absolute marvel of engineering, so let's get right into it.
Okay, let's dive into the core logistical problem here. Picture a massive container ship or an oil tanker stretching over 300 meters long. Deep inside the belly of that hull sits a giant prime mover, usually a massive diesel engine or a steam turbine. Now that engine is generating an enormous amount of power, but it's sitting essentially right in the middle of the ship. So how does every single ounce of that thrust originating far inside the vessel physically reach the water at the stern to push the ship forward? I mean, it's a huge physical gap to bridge.
Well, the answer is kind of mind-blowing. It all rests on a single spinning shaft. It's truly one of the most elegant pieces of mechanical engineering hiding in plain sight. Every single ounce of thrust pushing that massive ship through the ocean has to travel through this one rotating metal line. And we're talking about a shaft that is often 50 meters or more in length before it even reaches the propeller. But as you'll see, this shaft doesn't just spin, it also has to push.
Here is the exact path we're taking today. First, engine power. Second, intermediate shafting. Third, the thrust block. Fourth, the stern tube boundary. And finally, propeller output.
All right, Section 1, spanning the distance and carrying torque.
So the rotational power leaves the engine, whether that's straight from a slow-speed diesel or out of a reduction gearbox, and starts its long trip toward the back of the ship. In simple terms, this intermediate shafting is basically a very long, very heavy, and incredibly strong rotating metal rod. Now, because of its massive length and weight, it obviously can't just hang in midair. It needs support. That's exactly where tunnel bearings come in. Think of tunnel bearings sort of like supporting a really long broomstick with your hands at regular intervals so it doesn't bend or sag in the middle. These bearing shells support the shaft's enormous weight, allowing it to reliably carry torque over those long distances.
Now, marine engineers don't mess around here. They have incredibly strict rules of thumb for these shafts. The spacing between those tunnel bearings isn't just random. It is precisely calculated to keep shaft deflection, or sag, within super tight limits. And why does that matter? Well, if you have too much unsupported span, the shaft's own immense weight will cause it to bow slightly. When a bowed shaft spins at high speeds, it creates violent, dangerous vibrations throughout the entire ship. And that sagging, it inevitably leads to premature bearing wear and potentially a catastrophic failure of the whole system.
Moving right along to Section 2, pushing the hull, or what I like to call the climax of thrust.
Okay, so we've carried the rotational torque down the tunnel, which brings us to the most crucial and honestly the most counterintuitive component in the entire setup. Here is something most people completely miss. The propeller? It doesn't actually push the ship directly. No way, it pushes the shaft. Think of it like putting your shoulder against a wall while your arms push a heavy shopping cart. The cart, which represents the propeller here, generates the push. But it's the contact point at your shoulder transferring that push into your body that actually moves you backward. In a ship, that shoulder is the thrust block.
And this perfectly illustrates the mechanics of it. The thrust block is a dedicated, heavily reinforced bearing assembly. It features a thrust collar machined right onto the shaft itself, and pressing against that collar are thin, curved components called tilting pads. These pads rock slightly to maintain a crucial, microscopic film of oil under immense load. The thrust block is literally the exact point, the single component, that transfers the propeller's pushing force directly into the ship's hull structure. Without it, the propeller would just shove the shaft straight forward into the engine.
Let's actually test this concept out. Imagine you're out at sea and the thrust block fails completely while the ship is cruising along. What actually happens? Does the propeller just stop working? Take a second to think about the mechanics we just walked through.
Here's the wild part. The propeller keeps spinning perfectly fine, but the ship completely stops moving. The engine is still generating power, the shaft is still turning, and the propeller is still churning water. But because the thrust block has failed, that pushing force is no longer being transferred into the hull of the ship. It's a really subtle but absolutely critical distinction in marine engineering between making power and actually using power.
All right, on to Section 3. Keeping the ocean out, the boundary at the stern.
Moving further aft, we hit our next major hurdle. We have this huge spinning shaft, and eventually it has to physically exit the watertight hull of the ship and go out into the sea. That boundary is managed by the stern tube. The stern tube is the final sealed section where the tail shaft leaves the hull. To make sure the sea doesn't just flood right in around this spinning piece of metal, marine engineers use super sophisticated oil-lubricated lip or face seals. Basically, to guarantee the ocean stays out, the oil pressure inside the stern tube is kept slightly higher than the static seawater pressure outside. Because the pressure pushes out, the seawater literally can't push its way in. But man, when things go wrong here, the stakes are incredibly high. A stern tube seal failure allows seawater to ingress straight into the lubricating oil, which destroys the bearings. Or, conversely, it allows the ship's oil to leak out into the sea, creating a massive environmental hazard. On a ship, this is treated as a critical defect, requiring immediate repair. It is absolutely never a let's just monitor this and see kind of situation. It directly threatens both the watertight integrity and the mechanical survival of the whole vessel.
Which brings us to Section 4, Propellers and Pitch, delivering the output.
Finally, we reach the end of the line, out in the open water, where the rotational power we've been tracking finally meets the ocean. Now, there are two main ways to deliver this output. First, you've got fixed-pitch propellers. These are typically one solid piece of cast metal. They are simple, super robust, and highly efficient at their one-designed cruising speed. But to reverse the ship, you have to physically stop and reverse the massive engine itself. On the flip side, we have controllable pitch propellers. These feature an internal hydraulic servo motor inside the hub that can instantly rotate the angle of each individual blade. This lets a captain, like on a highly maneuverable ferry or a tugboat, go from full ahead to full astern in seconds simply by changing the pitch of the blades. No need to stop or reverse the engine at all.
Of course, pushing water around at high speeds definitely has its physical limits, and one of the biggest is cavitation. Cavitation is the forming and violent bursting of vapor-filled cavities, basically bubbles, on the back of a highly loaded propeller blade due to extreme pressure drops. When these bubbles collapse, they don't just pop gently, they do so with incredible force. Over time, this leads to crazy loud noise, severe vibration, and actual physical erosion of the solid metal blade. It's a pretty stark reminder of the immense hydrodynamic forces at play out there.
So let's take a quick step back and look at the whole shebang from input to outcome. Rotational power leaves the engine. The intermediate shaft, held up by tunnel bearings, carries that torque over distance. The absolutely crucial thrust block takes that forward push and transfers it directly to the hull. The stern tube seals keep the ocean out while letting the spinning shaft through. And finally, the propeller moves the water. It's a beautifully unbroken chain of precision engineering.
But this leaves us with one last incredible thought. Once you can generate thousands of tons of thrust and safely transmit it through a spinning shaft to move a 300-meter steel city through the water, how on earth do you steer it? How do you precisely direct all that force against the massive hydrodynamic resistance of the ocean using just a single rudder? Well, that is a fascinating question about steering gear, and it's exactly what we'll be exploring in our next explainer. Until then, keep questioning how the world around you actually works.